In the late 1920s, the godfather of the atomic bomb, Enrico Fermi, was researching how a neutron decays. This was when he noticed something unusual. When a neutron decays, it falls apart into a proton, an electron, and a mysterious particle, with unexplained forces accompanying it. For years, much of Fermi's research was kept a secret until now, when scientists at Cern reopened that door, and what is behind it could affect more than just our planet. With ominous global events occurring with suspicious timings, we must ask ourselves, are we at the brink of unleashing powers far beyond our control? And could this research reveal something that can make the atomic bomb look like child's play in comparison? During Enrico Fermi's research, he noticed that what he was observing when a neutron decayed could not be explained using the known particles at the time. This mysterious extra particle belonged to a different group of particles, with opposite charges of the ordinary matter surrounding us. Thus, it was named antimatter. While it's not something that seems important, it has a crucial role in our understanding of the beginning of the universe, and scientists are convinced it holds secrets that will completely revolutionize our understanding of the core principles of physics. Both matter and antimatter have identical properties except for their opposite electric charge, which means they should be equal and opposite, like a mirror image of each other, and yet, we don't really see much antimatter in our universe. And here is the problem: when matter and antimatter interact, they violently annihilate each other, leaving behind nothing but pure energy. If that's the case, and they are indeed equal and opposite, then shouldn't our universe have annihilated itself? This apparent inequality has been a mystery that has perplexed our world's greatest minds for decades. Fermi's research showed that while these particles do appear to be the inverse of ordinary matter, they certainly weren't acting like it. Not only that, but the math was not adding up. There had to be a force that wasn't accounted for, so he proposed the existence of a new type of force, the weak interaction, that affects only subatomic particles. But as he analyzed the way they interacted with each other, an incredibly polarizing discovery was made: either the theories of conservation of energy were wrong, which left a massive hole in everything science has built up to, or particles don't behave as we expected them to, and this mysterious force would be the start to a whole new area of science. This discrepancy, known as the Fermi puzzle, remained unresolved for several years until 1956, when two scientists developed a theory that could account for this, but it was a controversial one: particles and their antiparticles, contrary to expectations, don't behave the same. The subatomic world is, in fact, not symmetric. In other words, if a system is CP-symmetric, then particles and their antiparticles should behave the same, just with opposite charges. But in some instances, this symmetry is violated, and the laws of physics behave differently for these particles, known as CP violation. This major breakthrough in particle physics led to a better understanding of the asymmetry problem. Scientists realized that CP violation could be the key to explaining the imbalance of matter in our universe, but more crucially, it could explain why our universe even exists in the first place. To answer this, they would need to revolutionize science again, and a major collaborative effort led to the construction of the world's largest scientific project, the Large Hadron Collider. The world's largest and most powerful particle accelerator is located at the Cern facility in Geneva. Comprising a 17-mile ring of superconducting magnets, the LHC has a series of accelerators that fire high-energy particles through the apparatus at light speed. The resulting collisions produce a complex spray of particles, some with a lifetime of less than a second, that leave a trail of subatomic breadcrumbs that scientists can follow. Scientists rely on two highly complex detectors, including the Atlas detector, which is about 148 feet long and 82 feet tall, to detect and analyze these particles. This machine, weighing in at twice the weight of the Eiffel Tower in Paris, was instrumental in discovering the Higgs boson. Additionally, scientists at Cern use the Atlas detector with other detectors, including ALICE, CMS, LHCb, and LHCf. In 2013, the LHCb detector made a groundbreaking discovery in the study of CP violation. The sensor observed the decay of particles called B0 mesons into pairs of muons, which are, simply put, heavier versions of electrons. Moreover, the LHCb team found that the decay rate of B0 mesons into muon pairs was slightly higher than that of B0 mesons into pairs of antimuons and was not equal, which would be the case if they were symmetrical. Conclusive proof that CP violation is a real factor and that antiparticles aren't mirrored images of their counterparts. This observation was a significant breakthrough not just in the area of CP violation, but it also opened the door to the possibility of discovering new physics beyond the standard model of particle physics. With piqued curiosity, scientists also dove into researching a possible link between CP violation and magnetic monopoles, which have only been presumed to exist. Magnetic monopoles are hypothetical particles that are thought to have only one magnetic pole, either a north or a south pole, unlike traditional magnets, which have both north-south dipoles. If magnetic monopoles exist, they could help explain several puzzling physics questions. While Cern's search for magnetic monopoles began in the 1980s, researchers used the superproton synchrotron to look for evidence of these elusive particles. The SPS is a particle accelerator capable of colliding protons at high energies, and it was used to search for the signature of magnetic monopoles in the debris created by these collisions. But this search proved to be in vain, as no conclusive results were discovered. But now, with the Large Hadron Collider at their fingertips, scientists could finally complete their search for magnetic monopoles. By colliding protons at higher energies than the SPS, they hoped to find the missing piece of the puzzle. In 2022, scientists were eager to explore new theories and conduct experiments that could uncover the secrets of the quantum world. They believed that this could result in remarkable discoveries that would have a profound impact on the planet. However, this was when disaster struck. It was supposed to be the first test run after a 3-year break, but just a few days after starting up, the world rippled with fear as Cern made a terrifying announcement. Only it wasn't a scientific revelation but an unexplainable phenomenon. The Earth's magnetic field had cracked and stayed open for over 14 hours, exposing the world to large amounts of cosmic radiation and leaving scientists around the globe stunned. While it resulted in mesmerizing auroras, it also meant that we were vulnerable to solar flares and coronal mass ejections. Large coronal mass ejections can cause technological malfunctions that are especially troublesome in our current world. For instance, the Carrington event in 1859 disrupted the global telegraph system, and there are reports of operators receiving electric shocks and sparks from telegraph machines, igniting papers. Havoc causing coronal mass ejections can trigger a range of problems for Earth's technological infrastructure, particularly power grids, GPS systems, and communications satellites. When a CME event occurs, electrical currents surge through power grids, leading to widespread blackouts. At the same time, the Earth's magnetic field gets jostled, disrupting radio transmissions and increasing radio static in the ionosphere. This makes GPS systems particularly vulnerable to ionosphere disturbances, leading to GPS coordinates straying by tens of feet. The ionosphere layer contains charged plasma that bends the path of the GPS signal in the same way that lenses bend light, and GPS systems usually compensate for this bending to preserve accuracy. However, severe disruptions to the ionosphere during a CME event can render GPS models incapable of keeping track of the changes, and receivers cannot calculate an accurate position. Earth-orbiting satellites are also at risk during CMEs, particularly those in high geosynchronous orbits, where most communications satellites are located. Such satellites can be struck by a high current discharged into the satellite, or damaged when high-energy particles penetrate the satellite. When a CME triggers a geomagnetic storm, vulnerable satellites may be put into safe mode to prevent electronic damage. However, if an event such as the 1859 storm were to happen today, the damage would be massive. It would be an event that would set civilization back by decades. Furthermore, losing the Earth's magnetic field could lead to losing the air we breathe. The sun's natural wind is so mighty that it can easily rip gases from a planet's atmosphere until no gas is left. Mars is most likely an example of what happens to a world without a magnetic field. Its atmosphere was utterly unprotected and was ripped away into space when its atmospheric pressure fell low enough. It's entirely possible that without our geomagnetic field, our atmosphere, oceans, and life on Earth would perish in the same way. Regardless, this is an important area of research because it has broad implications for our knowledge of the fundamental properties of the universe. Furthermore, things like CP violation have practical applications beyond theoretical physics, such as developing technologies like quantum computing, which relies on the behavior of particles at the quantum level. Understanding CP violation could also have applications in developing new materials in medicine, which could help improve imaging techniques or develop new therapies. The experiments taking place at Cern are exploring a realm of physics that is shrouded in mystery. While we don't know what the tests will reveal, it's possible that they will challenge our current knowledge and lead to unexpected breakthroughs. As always, thanks for watching our videos. See you in the next one.